Welcome, everyone. I'm Jeff Biggin. It's my pleasure to introduce our speaker today, John from the University of Maryland. John got his PhD at the University of Washington Science and Engineering Department. I thought I would read, I really like this line from his bio about his research with the Makeability Lab. Focuses on designing and studying novel interactive experiences that cross between bits and atoms, the virtual and physical, and back again in front of the world's greatest challenges in environmental sustainability, health and wellness, education, and accessibility.
Awesome. I couldn't have said that better myself. Thank you, Jeff. It's really a pleasure to be here. This is my first time to Carnegie Mellon, first time to Pittsburgh. I drove up last night from DC, and it's only 4 hours away. My talk is going to be in 3 parts, but mainly 2 parts. The first part, I'm just going to introduce you to me and my group. And the second part, I'm going to talk about the main topic, which is embodied by my title slide. And then if there's time, maybe we'll talk about other things. All right? So, as Jeff indicated, this is my group. I'm in my 3rd year as faculty. We call ourselves the Makeability Lab, which we collectively decided would be a good name. And it is a lablet within the HCIL. The HCIL is the Human-Computer Interaction Lab. How fitting. Some of you might be familiar with it. It's one of the oldest human-computer interaction labs in the whole world. And it was started by Professor Ben Schneiderman back in 1983, so about 31 years ago. It's comprised of multiple disciplines, as HCI is. The cool thing is we're all co-located in the same space, so we have computer scientists, faculty, students, and staff from the iSchool, from education, psychology, and English and journalism. Computational journalism, Nicholas Diakopoulos is one of our newest hires. And so we're all in this shared space. And the one thing we lacked, though, which I noticed you guys have a lot of, is prototyping space. So when I started there, I built the HCIL hackerspace. It's now kind of on its 3rd version. This is what it looks like. It supports about 6 to 8 students working, and there's different kinds of stations. Like we have 3 soldering stations, we have a craft and textile station, and then we basically equip it with all sorts of materials to allow to support creative physical making, like mannequins, a wall of electronics, quadcopters, 3D printers, the CNC machine. And really, as the kind of bio indicated, we're looking at physical making and intersection with electronics making. So for example, e-textiles, which has been a big research arm that I won't really get into today unless there's time, but it's something that we've explored a lot in my group. And the fun thing is, you get to make, which is great, and you also get to experience new kinds of machinery and equipment, like sewing. So my students oftentimes sew, and also have a lot of fun, which I think is really important to innovation. So my group, we really try to have fun while we're doing things. This is like one of my first 3D printers. Like, oh, this is all amazing. So you guys should come visit. It's about a 4-hour drive. Or you can take the bus, or you can take a train. Okay. So let's talk about the main title of my talk, which is really crowdsourcing accessibility at scale. So let me motivate this a little bit. 30.6 million US adults have some form of disability that affects their ambulatory activities. About 15.2 use some kind of assistive aid. So, no problem. Some kind of assistive aid, like 11.6 million use crutches, cane, walker, and 3.6 million are in a wheelchair. The problem is, despite comprehensive US legislation, the world itself is still very inaccessible. Streets, sidewalks, businesses, which is really captured by this photo. And the issue is not just that this affects how people can get around, but also that there's no real information source for learning about the accessible parts of a city. And in fact, for example, the National Council on Disability noted that there's no comprehensive information on the degree to which sidewalks are accessible in cities. And this is a significant problem. It affects mobility, and it affects the independence of a large swath of people. From our own formative work, we found this also to be true. This is a quote from a participant with congenital polyneuropathy who says, "I usually don't go to where I don't know about accessible routes." And a more dire kind of motivation is captured by this newspaper article. Right? I also found a YouTube video that just sort of illustrates the danger of the lack of an accessible world. So did you see that? to me, my heart stops. Right? I mean, that can be potentially fatal. And so our vision really is to transform the way we can collect data about the accessibility of the physical world, and also to build tools, new kinds of tools that enable people to learn about the accessibility of the physical world. So I want to just show you two mock-ups. These are two kind of envisionments of what this future might look like. This is a little bit like WalkScore or WalkShed. It's a walkability type tool, and it's visualizing the accessibility of neighborhoods and cities. So the red parts are least accessible, and the green parts are most accessible. And you can also set different parameters about your mobility impairment, as well as things like proximity to accessible transit. And the visualizations would respond accordingly. This is just a mock-up. Okay? You can also select an address. Okay? And it would give you some kind of aggregate calculation. So in this case, the selected place has an aggregate score of 67 out of 100, primarily because 28% of nearby intersections lack curb ramps. So to me, this can be really powerful and impactful, and it offers some potential, like changing the way people think about and understanding their neighborhoods. It also might shift property values if we had access to this data, or fundamentally change the way where people live. For example, caretakers. Maybe if you're caring for a parent or a child who has some kind of mobility impairment, it might affect where you choose to live. And also, it could potentially change how governments and citizens make infrastructural investments. Right? It's probably not going to change how you route and move about the world, though. For this, we would need a different kind of tool. Something that we've been playing around with is accessible aware navigation. You can imagine a tool like this where you set your mobility level again and you get specific routes that are known to be accessible, and then various warnings. Like here, where we selected this warning, it's a surface problem that tells you a little bit of information about that. So for both of these envisionments, though, we need data, right? And lots of it. So this whole question becomes, well, where are we going to get that data? Well, traditionally, this data is gained from walkability audits, which are often done with an expert surveyor, and along with civic participation, right? And you fill out a checklist. So the cool thing is, this results in high-quality data, but it's very laborious, as you have to move about the physical world and actually do these checklists, and it's time-consuming and expensive. So other people have looked at these mobile reporting tools, like this is NYC's 311 app, where you can select, they call it a complaint, but you can make a report and even, for example, report a broken sidewalk in situ by taking like a picture. The most popular of these tools is See, Click, Fix. Some of you might be familiar with this. But in both cases, these sorts of tools require in situ inquiry. Okay, you have to be there. You're supposed to be reporting on what you physically experienced, which I think limits scalability. And they're also not specifically designed for accessibility data collection. And so for my last piece of related work, there are some emerging tools that are specifically focused on accessibility. Most popular are wheelmap.org and accessmap.com. But again, so they first focus on businesses and not streets and sidewalks, not street-level accessibility. And the second part is their model is still to report on something that you physically experienced, which again limits scalability. So our approach is different. We want to see if Google Street View can be a viable source of collecting massive amounts of data on accessibility in the physical world. And so there's a number of high-level research questions here. Can we use Google Street View for this? Is this viable? Can we create interactive systems to allow remote inquiry and remote labeling of these sorts of things? And finally, how can we use computation and automated methods to kind of scale up our approach? So I've been basically working on this since I started as faculty at the University of Maryland, and we published a number of papers on this topic, and I'm going to go through 3 of them. The first, which we did, is an asset poster, which is important to kind of go through because it has some principles that we end up using for the other papers that we published. So here we had, first this question of viability. We explored that, and then we also examined the effect of 3 different labeling interfaces. What we want is high-speed performance, quick labels, but also accurate labels. Okay? So it looks like this. This is our web labeling tool, one of the first versions of it. And there's 4 steps to it. First, we have to find and mark an accessibility problem. So this is a visual search problem. You have to find an accessibility issue in an image. You have to select a problem category. You have to rate its severity. And then you submit a completed image. So let me show you a snippet of our tutorial video that we showed crowd workers.
Your job is to find and label all sidewalk-related problems. In this case, there is a fire hydrant in the sidewalk, so you draw an outline around it. Outlines are drawn by clicking around the identified problem to set outline points, with a final click at the original point to complete the shape. When the shape is complete, you select the appropriate label. In this case, we select object and path, and then mark its severity. Severity is a 5-point scale where the far right is most severe, indicating non-passable, and the far left is least severe, indicating passable for wheelchair users. Here, we mark 5 because it is clear that a wheelchair user could not get past this fire hydrant. Let's look at a few more examples. In this example, the sidewalk is badly cracked. So again, we draw an outline by clicking points around the offending area. In this case, rather than selecting object and path for our label like last time, we select surface problem. It's also a less severe problem than before, so we select a 3, which indicates that the area is hard to pass for wheelchair users. For our third example, the sidewalk ends abruptly in the grass. This may force wheelchair users to tread along the road. So we draw an outline around the end of the sidewalk and select prematurely ending sidewalk, and mark 5 for not passable because the sidewalk ends in grass and on a hill. Finally, for our last example, a curb ramp is missing at this intersection, which would prevent wheelchair users from crossing the road. Note, you do not need to provide a severity for the label curb ramp missing. As you label these images, please know that there could be more than one problem in an image as shown here. You should try to label all problems in each image. If you are confused about a label, you can move your mouse over the 4 thumbnails on the right side of our interface. Here, we describe each of the 4 labels in more detail. You can skip an image if you are not sure about what problems to label. You will then be provided with another image to work on. If you do not find any problems in the image, submit without any labels.
Okay, so that was the outline interface. We developed 3, in parallel, we developed 3 different labeling interfaces which offer different levels of pixel granularity and also different levels of expected speed of performance. So point and click, a rectangular outline, and then a polygonal outline interface, which is what I showed you in the video. We collected this initial data set. This was manually curated. There was static screenshots of Google Streetview images. And we tried to make it relatively balanced. So we had 34 images with no curb ramps, 29 with surface problems, 27 with object and path, and 11 with sidewalk ending. We also had 19 images with no problems, so that we could look at false positive labeling behavior. Okay. So where did this data come from? Well, it actually came from ground truth. So I'm going to show you what we did. So here is an example image. If you guys were on our research team and you were trying to provide ground truth for us, you'd have to label this image. So let's do it together. What do we see? Double object and path, and one other thing. Yeah, which is indicated by that crosswalk, right? So this is a very highly inaccessible area, right? And that's basically what we did as a research team. So in this case, researcher 1 got everything. Researcher 2, and I'm sorry about the colors, hopefully you can see the difference. They missed out on that curb ramp there, and then researcher 3 got everything. Okay? And there's different ways we can examine these labels. One is at the image level. Okay. At the image level, this table tells us what problems exist. But we can also look at the pixel level. Right? And so these different levels of granularity allow us to localize the problem, and also our expectation was, and I'll show you later in this talk, that we could use pixel level labels to train a machine learning algorithm to start doing some of this automatically. Right? So that pixel level data was really important to us. So in terms of the localization, you can imagine at the image level you get about this level of localization, but at the pixel level it becomes a little bit more isolated. Right? Okay. And there's also a different specification, which is basically class specification. Here we can do binary, either there is an accessibility problem or there's not, and then the subclasses of those problems. Right? So those are the kinds of things that we use to evaluate. Here's the multi-class label, and then those are collapsed into a binary classification. Right? Either there is a problem or there isn't. And then finally we use majority vote, which is, if you've done crowdsourcing work, it's a very, very common form of quality control, and we used it in our ground truth. So here we had 2 people who marked this as prematurely ending sidewalk, and another researcher who said, well, that looks like a surface problem, and while that might be true, they got outvoted. Okay, so our ground truth data set would just look like what's in that column there. All right? So in our initial study, we posted all 3 of our labeling interfaces. We hired mechanical Turkers, 7 workers per image, and 3 to 5 cents per hit, 132 unique workers, over 2,000 assignments, and we gathered a total of over 4,000 labels. So So the two main findings here are accuracy and speed. So all three interfaces performed similarly. Higher is better here, around 80%. And that's without any quality control and minimal training. They only kind of watch our video tutorial. In terms of speed, as expected, point and click would be the fastest, and it is. It's 26% faster than outline. Interestingly, outline outperforms rectangle, which you wouldn't expect. It has more clicking with outline. It's a more complex task. But outlining is great for us because remember, again, we want to eventually train some computer vision algorithms. So we went with that for the rest of our interfaces. So in summary, the contributions of this first work was, sort of demonstrating the viability of this technique and showing that kind of point and click is the fastest, but outlining isn't really that bad either and gives you a lot more pixel granularity. Okay. Now I want to transition to this next piece of work where we really scaled up the things that we were doing in the assets paper, and which allowed us to look at a number of other kinds of sub-questions, like the accuracy of this work as a function of the number of turkers per image, different kinds of quality control mechanisms, and really gain a qualitative understanding of what makes this task hard. So most of you did okay when I asked you how to perform it, but what does it look like when turkers perform well, and what does it look like when they perform poorly? We also validated our technique for ground truth production. Okay, so we expanded our data set here to 229 images. And let's start here with the second point. So how good is our ground truth? And one way that we looked at this is we compared our labels, our ground truth labels, to sidewalk accessibility experts, in this case, participants in wheelchairs, 3 participants in wheelchairs. We ran an in-lab study like this, okay, and used splices kappa to measure agreement between wheelchair users and researchers. So here's an example from the study session. In this case, the person in a wheelchair also has a motor impairment, so the research assistant is actually doing some of the outlining for them.
Okay. Definitely this utility pulls an object in path. Okay, object in path. That's it, that's 5.
So it looked like that, okay? So in summary, there was strong agreement between the wheelchair users and the ground truth and the research team, which is good. And in interviews, further validating GSV or Google Street View as a data source, one person mentioned that they actually used it, to sort of virtually explore an area before they traveled to it. Okay. All right, now let's go towards our expanding on our Assets 2012 study. Here again, we used Mechanical Turk. We used more images and more people. We added crowd verification, and we recruited 28 turkers per image so we could begin to investigate quality as a function of the number of turkers per image. So this is what the labeling interface looked like. Okay, and then again, very commonly in crowdsourcing work, you'll see these verification interfaces, right? And here we ask about the labels themselves, and we also ask about the severity of those labels. So here's a quick movie. So do you agree with the severity rating as well? So we gather that kind of information. Okay. So in summary, we hired 185 unique workers, over 7,500 labels or labeling tasks, over 13,000 labels. We also had these verifications. These are 279 new workers, right? So this is a lot of data that we're gathering, and nearly 20,000 verifications. Now, as expected, verifying something is far faster and easier than labeling something. It's both cognitively easier because you don't have to go through this visual search time of finding and marking an image, and it also just requires pointing and clicking, right, on things rather than labeling. So in summary here, we have about 80% accuracy again, just like with the asset study. But this is, again, without quality control. With quality control, we boosted this to about 93% accuracy. So I want to go through some of the data qualitatively with you first, before I go into some of the quantitative graphs. Okay. So what do we see here? Missing curb ramp, right, or a curb cut. There's missing one in each direction. And this is with 28 turkers. I'm showing all the labels at the same time. And they did pretty well. Okay. Here's another example. Whole object and path. Okay. Even a few saw this part as well. Here's another premature landing sidewalk. I don't know if the city is like, oh, we got to do a sidewalk, and we ran out of money. That's it. Call it a day. Or they're like punching out and then they forgot all about it. I don't know exactly. They're all over the place. And it's interesting too to see the style of label. Like some people are kind of drawing in the sidewalk. Right? This is how it should look. Surface problems. This one's over by my house in DC, where I used to live. Sometimes they get really complicated, like there's a surface problem here and also kind of a crony curve ramp, and there's all kinds of problems in that image. Okay, so now failures. So if you've done any crowdsourcing work, you know that humans aren't perfect. In fact, all of you guys should know, since you're in the HCI, humans are not perfect. So in this case, we have a missing curve ramp. Okay, but since our task is to label problems, people start to see problems everywhere, including this stop sign, which I would offer is not actually an accessibility problem, right? It's in the grass. It's over on the side, but still it got labels. We had 3 people, there's no problems in this image, but yet people saw problems everywhere. I don't know, here, right? You know, so how do you deal with that? Well, we used majority vote, and so we recruited 28 Turkers to label each image just so we could experimentally look at different combinations of majority vote. So with 1 Turker, okay, I'm going to show you multi-class first. With 1 Turker, we had about 80% accuracy. You would expect this graph to go up as you hire more people, and that's what happened. So this is multi-class accuracy. So if you want to hire 9 Turkers, you can get about 90% accuracy. There is some saturation around 5. Okay. And our standard error kind of demonstrates that this is probably a generalizable result, since we recruited so many Turkers per image. We can also look at binary accuracy, and again, this is a slightly similar problem. Did people, did they confuse the kind of problem categories and just generally find problems? So yes, marginally, our results are slightly better. Yes, Jeff?
So I think I can probably just consider that. When you do the majority vote, so if you're comparing 2 workers' inputs, it's just if they found the same class of problem in the same image, or do you actually look at the regions?
So I'm not going to get into, so Jeff's question is, do you, when you're doing majority vote, do you look at just the class of problems that were identified in the image, or do you actually look at the pixel level agreement? And we did both, and we report on both in the paper, but I'm only talking about one, which is image level analysis, just to keep things simple. I'll talk about pixel level in the next part of my talk. We also evaluated a range of different kinds of quality control mechanisms. Many of these are fairly simple, and what you'll notice is, again, an increase. If you hire 3 labelers plus 3 verifiers, you can get about that 93%. Right? And again, here in summary, we have further validation of this idea. We further validated our ground truth labeling approach, and we assessed different kinds of quality control mechanisms. Now, I move on to our most recent part of the research, and to me the most exciting. So all of the stuff I've shown you so far is just relying purely on manual work, which I think we'd all agree doesn't really scale, right? There's a lot of work here. So how do we intelligently combine manual labor and computation? This is a fairly hot topic. There's a new conference called Human Computation. A number of people are starting to explore this. For example, in automatic workflow, so you might try to identify that a certain task or a subpart of a task is hard and hire more workers on that task. There's also been a number of recent work on using computer vision in Google Streetview. So for example, Goodfellow et al., this is at Google, they're looking at using neural networks to automatically recognize street addresses, the digits in street addresses. Okay? So our system builds on and extends this work, but is applied to accessibility in the physical world. And specifically, we look at 4 design principles. First, computer vision is cheap, basically 0 cost. Second, manual verification, as we've seen, is far cheaper than manual labeling. Third, automatic curve ramp detection is hard and error-prone. Computer vision is an open research area, especially object identification. There's no way that we can generate a perfect model yet, right? And so we have to design our system around that. And fixing a false positive is easy. It's a matter of clicking and deleting a label. Fixing a false negative is hard. It means you actually have to apply a new label, right? So that's kind of the principle around Tome, which I'll get into the architecture in a second. But I want to point out that in this case, we're focusing specifically on curve ramps for this part of the talk. Okay? So it's comprised of 6 parts. We have a data scraper, which downloads GSV imagery and GIS data. We store things in a database. Then we have this automatic curve ramp detector, which again is going to make some errors. So here we have false positives. And then the more expensive thing to correct is a false negative. right? And to deal with this, then we designed a smart task allocator. So if we think that our computer vision algorithm or that computer vision subsystem didn't have any problems, then we're going to route the work to verification. If, though, there was an issue, we're going to route it to the manual labeling. Let me show you an example. So it comes out, we have a number of bounded boxes, this is our CV output, and so our smart task allocator looks at the CV output. It also looks at a number of characteristics of the image and the intersection, different contextual figures, like the connectivity of that intersection, so how many streets are going into the intersection. It's trying to derive the complexity metric and predict whether or not the CV algorithm failed. If there's no false negatives, then we'll just go right to our manual verifier. If we predict even one false negative, we throw everything away and we start over with manual labeling. All right? So quickly, I'll go through some parts of these systems. In this case, we really gathered a large data set. The web scraper looked at downloading Google Streetview panoramas as well as some GIS metadata. We also scraped 3D point cloud data, which the Google Streetview cars collect through LiDAR. That's not accessible when you just use Google Streetview, but it's something that you can download. And then we also did top-down map imagery, which I'll talk about how we use that in our smart task allocator. And because sidewalk infrastructure changes depending on which city you're in, we looked at 4 cities in North America. There's also regional differences. So whether or not you're in downtown versus a residential area, sidewalks look different. So we looked at different sources, different regions within those cities. In total, we had over 1,000 intersections, over nearly 3,000 curb ramps. Of the images had 647 missing curb ramps. And one thing that always comes up when I give this talk is, wait a second, Google Street View, they don't drive those cars every week, do they? So on average, our Google Street View data is 2.2 years old. Is that a problem? No, could be. Maybe some of you guys are already thinking that. So we went out and we actually, this is what happens when you're my graduate student. We went out and physically audited a subset of our data, just to compare, right? Well, the fact is actually curb ramp infrastructure doesn't change that much, okay? So this is our physical audit areas, 273 intersections in total. I actually did some of this physical auditing myself. And in summary, there is high agreement, okay? Because curb ramp infrastructure doesn't change that much. The few disagreements that we had were due to construction, okay? Perfect. All right, automatic curb ramp detection. This is the fun part. So can we build an automatic detector for finding curb ramps in these panoramas? We came up with a 3-stage process that starts with curb ramp detection, then we have some filtering, some post-processing, and then finally we have further refinement through a support vector machine. So we experimented with a lot of different computer vision approaches, and we decided upon a DPM, a deformable part model, which is one of the best performing object identification algorithms out there. And one cool part about it is, well, it uses a histogram of gradient features, but also has spatial information about where those histogram of gradients exist. So let me walk through a quick example. This is stage 1 of our output. Got a driveway, right? Some other things here. In the bottom corner, I'll show you how this changes over time. So we have multiple redundant detection boxes. And as I noted, curb ramps shouldn't be in the sky or on roofs, right? So we use non-maxima suppression on these redundant bounding boxes, and then we use that 3D data, which is fairly coarse-grained, to filter out things that are in the sky, for example, right? So that reduces it quite a bit, and then in stage 3 we do some other characteristics. We look at the size of the bounding boxes and their location in the image. There's a lot of geospatial properties with curb ramps. They're going to only occur in various locations, and we can sort of use that principle to further refine. Okay, so finally we have one true positive and a few false positives in this image. Here's another example. Okay. And here we have false positive detections and that false negative. And as I said, this false negative is hard to correct. It means we've got to have somebody go in there and label it. So it's expensive. All right. To evaluate this, we use twofold cross-validation. And this is a precision recall graph. We change the confidence threshold. And look how our precision recall changes. So with higher precision, we have less false positives. With higher recall, we have less false negatives. A good computer vision algorithm, maybe on something like facial detection, will look like this, or maybe even like this. And your goal is to maximize the area under the curve. In our case, we did better. It's like this. This is stage 1. And what your hope is that it's going to get better and better with our various stages, and they marginally do. Okay. One thing to notice, though, is even in the best case, like if we accepted very low precision, we're still missing 20% of the curve rims. Right? So the confidence threshold that we chose for the WISP paper was at negative 0.99, and the key point here is we sacrifice precision for higher recall. Okay? So curve ramp detection is a hard problem. And it would be lovely if more people were looking at these sorts of things, creating computer vision algorithms to automatically find accessibility issues. But there's a number of reasons why this is hard, like occlusion, illumination. These are common problems in computer vision. Scale, viewpoint variation. There's cross-classification similarity, and there's interclass classification issues as well. Right? So then the question is, well, can we infer challenging intersections? Is there some way that we can predict if a scene is hard? Right? And so that's really what the smart task allocator tries to do. It tries to determine whether or not computer vision is going to fail. And we look at a number of different kinds of features. We build a 23-dimensional feature vector that looks at things like the number of roads that are connected. We look at the 3D depth variance. So if there's a lot of 3D depth variance, then it's probably a more difficult intersection. Okay. And I'll show you our manual labeling interface first. So now you have zoom and pan. You can look all around the intersection. You track how far you are. So you have this observed area, and after you've looked at the entire area, you can submit the task. For verification, which again should be faster, it looks like this, and you just click on a label to delete it. And hopefully you can do this really fast. So, this is the key question. Can we beat, with these semi-automated methods, can we beat manual labeling alone? And so that's what we looked at. Our baseline was manual labeling with our custom interfaces. Then we also had CV verification, CV plus human verification, and then finally we had our system. Our two main measures, as usual, are accuracy and task completion time. And again, we used mTurk, and we had 1,046 GSV images, 40 were used for golden insertion. So some of the tasks, you didn't know this when you were performing the work, but some of the tasks we knew the answers to already, and then we would show you, and we'd give you feedback if you made an error, and hopefully you'd improve from that point. We, again, collected a lot of data from 242 distinct Turkers, and again, there was no overlap between verification users and the labeling users. So how did we do? Let's start with accuracy and cost. Again, accuracy, higher is better, cost, lower is better. So with manual labeling, we had about 80% accuracy. This is our baseline. And 94 seconds per intersection. This is with just manual labeling. With computer vision and manual verification, not doing as well. Accuracy drops, but our time is much faster, as you would expect. Okay, and here's the key question with Tome. How do we do in terms of accuracy? Well, very similar to the manual labeling approach, and at a 13% reduction in cost, which is marginally significant. It's a step in the right direction, I would offer. And in terms of our smart task allocator, which again is a trained system using supervised learning and lasso regression and SVM, 80% of the tasks that went to the verifier were correct, but only 50% that went to the labeler were correct. And we were very conservative because of the expense of false negative correction, so we were okay with this trade-off. We also looked at if the task allocator were perfect, what would be our performance improvement? And we would get a 28% performance improvement. So currently we're getting 11 to 13%, and we almost double to triple that. Okay. So this both points out that there's room for improvement in the task allocator, but also with a perfect task allocator, you're still not getting huge speed-ups, not orders of magnitude. And for that, we would need a lot more better refined computer vision algorithms, which we're also currently working on. Okay. So in summary, we offered the first computer vision system for automatically detecting curb ramps. We showed that automated methods could be used to improve labeling efficiency for curb ramps, and we've, again, validated Google Streetview with those physical audits. So in the future, we have a number of things that we'd like to look at, and I just want to give you a taste of it. But first, a back-of-the-envelope calculation. So I started out with this kind of access score visualization, that heat map visualization. So how far away are we from gathering all that data? Well, this is DC. Each one of those white dots is an intersection. There's 8,209 intersections in DC. Right? A little back of the envelope here. So if we used one of our custom interfaces just to do that remote labeling, it would take 214 hours, which, honestly, if we hired 214 Turkers, that's only 1 hour per, right? Or a half hour if we double that. Which told me this drops to 184 hours, and we think we can do better. This was our first shot. The other thing to point out is we actually don't know how long this takes. I mean, we track our physical auditing, but we don't know how long it takes a professional to move about the world, so that's something we're currently looking into. So in terms of computer vision, this is doing a 3D reconstruction of an interface. Something that we're not taking into account is context. As I mentioned, things like buildings, pedestrians, all of those things maybe can be used as contextual features. We also want to improve training because there's a lot of variance in curb ramps. We used an aggregate training data set, but we should probably split that once we get a larger data set. That is, DC should be trained on DC, and we didn't do that yet. Okay, and we also want to look at things like mensuration. Like, is this sidewalk actually wide enough? Is it 60 inches to support a wheelchair? Another thing we want to do is related to kind of citizen science, which we want to open this up to be a public website where people, volunteers, we think really it would take a motivated family member who wants to label maybe their whole neighborhood an evening of work to do that. So we want to release these, we want to refine some of the interfaces and release them out into the wild. And we're also exploring ways to improve our verification and labeling interfaces. So this is one idea we had, which this is called Quick Verify. It's supposed to allow for really rapid verification. It's kind of like Google Picasa, if you've seen that for their face recognition task, where you say yes, no, and you can do it really quickly. It turns out, in our pilot studies at least, it did not work effectively. Why? You need a lot more contextual features, right? So it's actually a hard problem to come up with different interfaces. So our current verification interface allows all of this navigation, which allows you to build context of what you're looking at. And without that, it's actually hard to figure out. Another thing we're super excited about is temporal tracking. Google Street View recently released, in all places that you visit, you can see the history of that place every time the car drove through. But you'll notice in DC, they've driven through there 8 times since 2007. So you're seeing some of how the infrastructure changes over time. And again, in order to study this, you need to have really scalable interfaces. But I'm really excited about this as a potential. So in this case, this hasn't changed out. Why? I don't know. This place is getting worse over time. It's turning into a field. You guys saw this one before. This is every 2 years. So they actually changed the pole design, but it's still like in the middle of the sidewalk. So these are all problems. Another thing that we've been kind of playing around with in our lab, I'm using drones in some of my other projects, is kind of robotic surveying. So you can imagine a drone going out and doing the surveying itself, or actually having it be basically an assistive aid attached to a wheelchair and going out and doing some of the surveying. Yes, Steve?
This is wonderful. I was going to ask the back of the envelope question, but you got to it first. But I'm wondering, have you thought much about the experience of the people who are in wheelchairs, how they would access this information? Is it just like an add-in to Google Street View, or?
That's a great question. So the question is, like, people in wheelchairs or others with mobility impairments, how would they get access to the information? I think maybe a mobile tool would be appropriate, or I think the ideal would be that it would be built into Apple Maps and Google Maps, just like you have now pedestrian routing and you have bike routing in some cities with Google Maps. I think that would be the ideal. I mean, it's got to get into that platform, and thankfully Google has been very supportive of this work. So I don't know. I mean, we're a ways away, I think, from it getting integrated, but I'm really excited about that future. Okay, so lots of people to thank. This is Kotaro Hara, who's my first PhD student, and the computer vision side was led by this graduate student, Jin Sun, along with David Jacobs. And one other thing that's cool is we've been working with a number of undergrads and also a high school student over there, Jonah. So this work was sponsored by Google and NSF and IBM. And since I have a bit more time, is there questions? Because I have the ability to pivot and talk about some electronic textiles if you guys are interested, but we can certainly take questions too. Yeah?
How is the marking adjusted when the view on like Google Street View would be, like if you're looking at it from a different perspective, is the system able to dynamically adjust?
So not yet. So basically we would treat that as independent labels, and I think that's really exciting. That's not something I covered in the computer vision part, but it's future work. One cool thing about the Google Street View card is it captures it actually continuously captures, but what they publish is about every 5 to 10 meters. So things like occlusion could potentially be solved because you're getting multiple angles, and that also would allow us to do some 3D reconstruction, which we're excited about. Another thing that we're hopeful is the Google cars keep getting better and better, and the LiDAR camera is set up now to scan buildings for like doing Google Earth texturing, but as soon as they have a more broad scope, then maybe we could start to use that 3D depth data actually to calculate things like whether or not there's a curve around. And we can't take that into account now because it's too coarse and it's pointed in the wrong place. Other questions? Yeah.
Have you thought about, nice work by the way, have you thought about a fully automated approach for the computer vision algorithm? Is that even possible? So,
Like, what do you mean?
So you're doing curve detection,
Yeah.
but you're handing off, if it fails for some reason, you're handing it off to the crowd.
Yeah.
Do you think it's possible to do 100% computer vision curve detection?
I
If
don't.
not, how do you do?
Not in my lifetime, and it's also, I mean, humans are not perfect at this task either. I mean, I didn't go into the the banalities of the ground truth process, but even if you were a trained member of my research team, you and I would have disagreements about some curve reps.
Right.
And so humans are going to make problem. They're not going to be perfect. Computer vision is not going to be perfect. That's why it's kind of fun to interplay there. I think is really so. I don't think computer vision is ever going to be perfect though. If there's any computer vision,
How close though? Like
I don't. That'd be a great question for David and his student. David's student's PhD would be awesome if he made some real significant.
You compared the speed of labeling versus verification.
Yeah.
What about the accuracy? Because with verification, you've got social pressure, so people are seeing a judgment that somebody else
Right.
made. So are they being influenced by what they saw?
That's a great question. I cut out some slides about showing you some areas where people failed at verification. We haven't explored it in depth, is kind of the short answer. The fact is, again, humans are not perfect, and so they're going to make mistakes with verification as well. We would get the elimination of true positive labels. And so you end up getting different precision and recall than you would expect, even with verification. So, and there's also another related question, which is how good is good to make some of the apps. Like I think the access score visualization doesn't require as good of accuracy maybe as the accessible route navigation. But since our tool is visual, I think one thing we want to do is with the route navigation thing is actually show pictures of the problem, so someone can self-assess. You're not offloading that onto computation. You can say, oh, you know what, that wouldn't be a problem for my particular mobility impairment. Yeah. Yep.
Hi. So I think this is really cool, and I like the idea that you said of somebody's family member could assess their own neighborhood really easily to make it a volunteer thing. But even if you've done the assessment, if you can wrap around it, the thing that you would actually want is maybe for the city to then come and fix those things to make it more accessible. So do you have any plans of
what a utopic vision you have of cities and governments? I mean, what's cool is when I was putting together the video for the temporal tracking was how much when we data collected for Assets 2012 and for Kai 2013, we marked all the locations so I could go back to those things and just sort of anecdotally seeing how many things have not changed. And governments tend to be reactive when it comes to accessibility. So DC is sort of the flagship city. I don't know if I can say that, but the federal city, they really try to do. I've talked to the ADA coordinator for the Department of Transportation in DC, and they really do invest a lot, especially in the downtown area. It's still not perfect, and it's highly reactive, right? They tend to not change things unless they get phone calls. Now, with the ADA legislation, if they do any street fixes, So if they come out and they do like a renovation on a street, they have to improve the sidewalks so that they're up to ADA compliance. But it's just slow changing. And so I still think it's really empowering to allow, it's an information problem for me. We get in our cars now, we get real-time traffic navigation, we get all this amazing, awesome data. Nothing like that exists for pedestrians with accessibility issues. And like, why not? Let's try it. That's what's exciting for me. Yeah, Jeff.
So we talked about something I think related to the points made about computer vision in some of our projects, which is unless the automated approach is able to take over a very large part, so if it's actually able to change the order of magnitude of the human labor, is it actually worth doing? Yeah. Because right now it seems like it doesn't cost that much. If you had volunteers somehow do it, or even people in wheelchairs themselves do it, they could cover DC pretty quickly. Yeah. And so is there actually value? And especially if we don't know if computer vision is going to be able to take over a significant part of the workload soon, is there value in doing it?
There's intellectual value. I think, yeah. I mean, really, let's say, to me, this is the exciting future, would be, what if we want to label literally like every single segment of Google Street View, which is up to like 1 million miles? I think we need to have some automated approaches. And I think to get there, maybe we need to have more than 1,100 intersections. We need to be at the scale, like I talked about this convolutional neural network thing about the digit recognition and addresses. Their data set is on the order of like 3 million. And it would be great to get up to that level so you can do fundamentally different approaches. I don't know. And plus, along the way, I think hopefully there's a lot of translatable, transformative knowledge that comes out of this. That's not just about Google Street View, but that's like computer vision, new kinds of computer vision algorithms. It's a good question, though, Walter.
Yeah. So actually, 2 questions. First, building on that point, do you have any sense of how many new intersections or how much intersection reconstruction was done during this data collection? So there might be actually construction in DC that makes this a continuous problem.
Yeah, so it's going to be a continuous problem, and cities change. And one thing that was really interesting with this, with the new feature in Google Street View, is to see how often cities change. So in my opinion, since Google has, Street View started in 2007, and since 2007 they have 8 captures in DC, and that says to me that they realize they need about a capture per year, and that's how much the cities change. And my expectation is with their automated cars and things, that there will be a time in our world where we'll be like, whoa, that image is like a week old, So it might be like a live stream. I know there's some startups too that are doing some basically daily flyover data in Silicon Valley. So I didn't talk about any top-down stuff that we're working on, but there's other kinds of data sources. Right. Did you have a second question?
I did have a second question. So people are actually really bad at sort of judging other people's accessibility needs.
Yeah, I agree.
So are workers actually good at assessing, kind of, you showed at the beginning, the severity?
Yeah, we've never actually evaluated severity, quite honestly. I'm not sure. That's a really good question. Part of Kotaro's thesis is to work with people who have mobility impairment and get their feedback about these things, and that's going to be like a chapter 3. Some more it's like little post hoc formative work, but it's really important. And ideally, we'd be doing this in participatory design the whole time to get more feedback about our tools. But one thing that I didn't really point out, which is a nuance, which is that severity scale was for the case of a wheelchair user. So, that was my first foray, was the Assets 2012 poster, and we used this tutorial video, which is not the way you train people. It's not the way you teach people. It was horrible. We actually forced them to watch it, forced. You couldn't see the interface until the video, but of course they probably alt-tab to something else. The way you train people is by what? Exercises. And so all of our new stuff is interactive training, which I know you guys do, I think, too. So you get dropped into a scene and it gets, it's like games. You download a game on your phone, it gets increasingly hard. And that's kind of what we do with our interactive training. And then we also, if you're not good, if you can't get past our training, then we don't watch you, basically. Yeah. So, yeah.
At one point during, when your system processes the images, you calculate the complexity metrics for a given intersection. And do you use those complexity metrics alone, or is it something Bayesian related to like the result of the processing, you know, the different rectangles that were tagged to determine whether there might be false positives?
Right. So I went over that pretty quickly. It's a great question. We use the Smart Task Allocator just uses 2 linear classifiers. It's looking for the CV output. That's some of the feature vector. It's looking at like the position of the bounding boxes, the size of the bounding boxes, those other things. It's also looking at other data that the computer vision subsystem doesn't take into account, like some of those complexity measures, like cardinality and other things. And I think there's a lot of, I'm more interested sort of in the computer vision part, but I think there's a ton of fruit in the task allocation as well. Yeah?
Yeah, you mentioned the concept of the crowdsourcing. So I think that till now, how many people or how many users, volunteers are involved in your research?
0. We haven't started that part yet. We haven't opened up, so we've only used mTurk labor. But like what I hope is, and there is a lot of, you can go to Zooniverse and you can see all these really cool citizen science projects, and some of them suffer. Like I showed wheelmap.org very early and accessmap.com. I suggest you go to those websites and you'll see that they suffer from a lot of critical mass issues. They don't have any data. Huge data sparsity problems. So we hope to bootstrap through mTurk always. And that's why I think allowing minimally trained people to do this is important. But we also hope that there will be a built-in audience. That once they hear about the tool, they'll be incentivized intrinsically to go out and hopefully label. And those labels will be high quality. And that's will be something that we can look at as like mTurk versus volunteer participatory labels, participation labels. Other questions? You guys aren't going to allow me to talk about my textiles.
I would love to know about textiles.
Yeah, I don't know. Dan?
Yeah, this is really cool. I'm thinking about this from on like a spectrum of like eventual once this is done, kind of end use case. When you go to Google Maps, it's got like a wheelchair option too. Kind of way it's got a bike option now, or a car option, or a walk option. But like, and I'm wondering like, will the modes of transportation grow too? You've got public transport. You might have like, I don't know, I ride a scooter, or I have a Vespa or moped.
I want to segue personalized route suggestion.
Right. Like I mean, it's silly, right? But Tiger probably would have done a lot better if we could do segue maps and see where we could get places.
Right.
Yeah. Does it go on forever? Like, or do you think it'll get into like 5 bins and that'll be it? Or?
Well, I do think accessible transit is another thing that's important. Mm-hmm. And so, like, we had on K Street, which is a very big street in DC, they put the bus stops in kind of a middle curb area with no curb ramps. So you could get off the bus on a wheelchair, and then you were stuck on this median, and there's no way off of those things. So we have started looking at applying this to other things like accessible transit. We had an assets paper that looked at bus stop accessibility for people with visual impairments and stuff like that. So I don't know. I hope that some of the things that we've been doing can generalize to other kinds of data collection. There's interest in public health, like in surveying the environment, like its walkability, like number of trees. With the temporal tracking stuff, you could sort of look at maybe some sustainability about trees and vegetation and stuff over time. So, I don't know. I mean, Kotaro could probably create this generalizable labeling tool.
I'm just wondering if you need so say next year they come out with something that's not a wheelchair, but it's a spider chair or something. That'll have a whole different profile of.
Yeah.
And I think this is sort of more a cool opportunity than a problem, because then you can solve the generalized routing problem for any kind of transportation that I use.
Right. Yeah. Yeah. Potentially. Yeah, Bob.
What are the downsides of restricting this to being accessibility, as opposed to the same way that the same curb cuts are useful for bikes and people with strollers?
Right.
The volunteer labor force that you could possibly get access to could be much larger.
Yeah.
This wasn't just for people with wheelchairs.
Yeah, I agree. And maybe we shouldn't call it like access score or something. That's a really interesting framing thing. I think usually when we motivate the work in our papers, we talk about situational impairments. I'm going to be a new dad soon. And so I will be, I will need to have those curb cuts if I want to walk around with the sun and so on. I think that's a really important point. And potentially it would allow us to kind of open up new avenues of participants who wouldn't otherwise be interested. That's great. Can I close with one video? Should we do that? It's going to be good. Quickly, there's flatulence, if I may. So Bob, that might make you stand. I know you have to. All right.
Our first prototype sense and visualize the user's heart rate. Wearers can also view their digestive organs. Prototype 2 added airflow visualizations and flattened organs. We informally elicited feedback from our co-designers and at our local mini maker fair. Prototype 3 offers new and additional sensing and visualization. The heart and lungs visualize wearers' live heart rate and breathing rate. The snack time button initiates the digestive system visualization.
This is a learning and inquiry tool for kids to learn about their bodies experientially through movement.
A video illustrates food breakdown in the stomach. In this case, we use an apple slice.
Smartphone stomach.
Sound effects indicate the end of digestion. Magnetic removable organs allow children to explore different layers of the human body.
And this is really important. We're using conductive magnets here because the body is layered.
Outlines and colored highlighters guide the reattachment of organs, which automatically begin working if placed in the proper position. We interviewed teachers and conducted single-session field deployments with children to gain feedback on our designs.
I officially want to be the only HII speaker ever to have flash limits in a talk, so I think that wraps things up for me.